Good afternoon. Can you hear me?
Yes, sir.
Yes, sir.
Let us continue. We'll discuss a new topic today on solution of the discretized equation. Okay. So your syllabus for the midterm exam is till the last class, till Monday's class, whatever was taught. So today's class will be in the final. From today onward, it will be in the final exam. Okay. You can see my notes, right?
Yes, sir.
Yes, sir.
Okay. So what we have seen till now in finite difference method or finite volume method, both the discretization methods is that we get some relations between the variable value, say variable is temperature, or it can be velocity u, velocity v, velocity w, or it is concentration c, or general variable phi. So whatever is the variable, we get a relation between the variable and its neighboring points. This we have seen in finite difference also. For example, we have written the derivatives for the point I in terms of the values at I minus 1 and I plus 1. Okay, so the neighboring points are there. If it was I comma j for a two-dimensional problem, then the equation had values of the variables at I minus 1 comma j, I plus 1 comma j, ij plus 1 and ij minus 1, as well as ij obviously. So similarly, in finite volume method also we have seen that for any point P, we have the east point. So P can be considered as the I point. East will be I plus 1 and west will be I minus 1. Okay. So we can write like this. If it is a 2D problem, you will be able to write in terms of the north as well as, means in addition to east and west, you will also have north and south. So it will be I plus 1j, I minus 1j, ij plus 1, ij minus 1, same thing. Okay. So ultimately, the only difference will be in terms of the coefficient values. And remember, at this point, we already know how to calculate the coefficient. Okay, whether it is finite difference or finite volume, we know how to calculate the coefficient. Okay. For example, for this case, coefficient is Ke by delta Xc. K is known, conductivity at the interface. We can use harmonic mean to find it. If it is constant, there is no issue at all. Delta Xc is known because it is a geometrical parameter which is calculated beforehand when creating the mesh. Similarly, this also is known. And SP also will be known because it's a given parameter. SC also is known. Delta X also known. Everything is known. All the coefficients are known. Only unknown are the temperature values here. Similarly, for all cases, the general variable phi will be unknown. Okay. And what will you have? You will have n equations and n unknowns. Now you want to solve these n equations to get the n unknowns. Okay. So what we have seen is that somewhere we have discussed some time back. Let me just see whether I can find it. Yes. So it was in finite difference method, but the same thing holds true for finite volume also. So we have, in this case, we had n minus 2 equations and n minus 2 unknowns because the boundary points we assume that are known. Okay. And we created a, we saw that we can write it in this matrix form, where this is the known as this coefficient matrix. This is a square matrix. If it is n unknowns and n equations, then this will be a square matrix of size n by n. Okay, n into n. And this is a column vector of size n if n unknowns are there. In this case, it was n minus 2 size. And this has all the known terms based on the source terms and other terms. In our case, this will have the terms related to B. Okay, these terms will be there. So we can express our equation in this form, in this matrix form. Okay, so I can write this as some coefficient matrix A into T is equal to K. Okay, I don't know whether I've written here, it's not visible, but A into T is equal to K, and we can, if we try to solve it, what we can do is T is equal to, so we can multiply this both sides by the inverse of A. Okay, so inverse A, T, which becomes identity matrix. So T is equal to A inverse K. Okay. This is solvable unless this matrix is singular, which means that the determinant is 0. Otherwise, this is solvable. Okay. If the determinant is 0, this anyway this equation does not have proper solution. So directly we can solve, obviously, when writing a program. Sometimes the software takes care of it. So for example, in MATLAB, if you write, you can directly invert and solve it. So MATLAB has its own optimization algorithm. It will optimize this matrix inversion and solve it very quickly. Okay. But if you are writing a general program where you want to do the solution instead of directly doing the matrix inversion through the software, say you are writing a C program or Fortran program, or you do not use a library, you are writing your own subroutine for that, then we have to know which method works best, okay, and how to solve this. So that is what we are going to discuss today. Okay. Numerical solution of linear algebraic equations. So we have n equations, n unknowns. How to find those value of those n unknowns? Okay. So there are two different methods: direct method and indirect or iterative method. We will study about the direct and iterative method both, but in direct method we will study about method which is known as tridiagonal matrix algorithm, which is widely used for solving CFD problems. Okay. There can be other methods like matrix inversion methods like Gaussian elimination. Okay. So we will not study that because that is numerically very expensive. Means it takes a lot of time. I will come to this discussion in a minute. The second type of method that we will discuss, again, those who have taken CFD course with me already knows these things because this entire syllabus is almost similar for both the cases. So iterative methods are the methods where you are not trying to find the solution in a single go. Means simultaneously you are not solving and finding the solution. You are finding some intermediate solution, again iterating, again finding intermediate solution, gradually going towards the correct solution. And we say that we have obtained our required solution when the change from one iteration to the next iteration is below a certain number, which is known as convergence factor, or like a tolerance. This is like a tolerance limit. Say if my required convergence factor is 10 to the power minus 6. So if the difference from one iteration to next iteration is less than 10 to the power minus 6, I say that, okay, this result is acceptable to me because the error seems to be very less. It is less than 10 to the power minus 6. So that small error I am not bothered with. That is acceptable. Or some other method I may use 10 to the power minus 3. That may be also acceptable for me. Okay. So there are different methods which we study: Jacobi method, Gauss-Seidel method, and then an extension of this direct method, TDMA, which we will see that is can be only used for one-dimensional problem. So we will extend it for 2D and 3D method, 2D and 3D problems by using some modifications, and this modified algorithm is known as line-by-line TDMA. Okay. So let us today discuss first about this direct method, TDMA. So before going into that, let me just explain why this we are not studying this Gaussian elimination. Anyway, you can just search Wikipedia and study about Gaussian elimination. It's nothing but it's like I think all of you have already studied it in your maths course. So if you have matrix, basically you reduce it to a triangular form. Okay. If you have matrix, the coefficient matrix, for example, in our case, which was a square matrix, you reduce it to a triangular form, and then from that the solution can be obtained easily. Okay. So, or if the matrix inversion can be done. So the main problem with this method is that this is going to work, but unless the determinant is 0, obviously. But the main problem is that the number of arithmetic operations that are required. Arithmetic operations are like subtraction, division, multiplication, addition, things like that. Okay. So one way of measuring the time required for your simulation to run. So when you are trying to solve a real life problem, say energy storage problem, we know that it will take a lot of time to run. But how can we estimate which method will lead to how much time? Okay. So one way of knowing this is to see what is the number of operations required for a particular step. For example, for solving this set of equations, how many arithmetic operations are required. So for Gaussian elimination, if you have n equations with n unknowns, you need of the order of n cube equations. Okay, not exactly n cube, of the order of n cube equations. Okay, exactly I don't remember, like 2n cube by 3, something like that, but it is of the order of n cube equation. Okay, and it means that, so we have not n cube equations, n cube operations, sorry, n cube operations. So say I have a 1D problem like this, heat transfer problem or fluid flow, whatever 1D problem is there, and I want to find the temperature, and I have divided this because I am trying to solve it by using a computer. Obviously, I will not divide it into only 5 points, because that will give me very crude solution, right? Very rough solution. I want to divide it into 100 point or 1000 point, so that we get temperature at very close frequency, so that we get a smooth curve. Okay, we get the correct approximation of the temperature instead of a very crude approximation. So if I divide this domain into 100 parts, okay, in the x direction, there is only one direction, x direction. If I divide this into 100 parts, then Gaussian elimination will take of the order of 100 cube arithmetic operations. So of the order of 1 million arithmetic operations will be required, okay, for solving. So it looks like a lot, but for a computer, it's done very quickly, because nowadays computational power is very large. But say 30 years back, it would have been a very big task. In 1990s or 1980s, it would have been a very big task. And nowadays it's easy, but slightly scale up the problem. So now instead of say 100 grid points, I want to refine it 10 times. I want to make 1000 grid points. Okay, so that I get much more accurate, much more close results, much more accurate results. I can approximate in a better way. Then suddenly you need 100,000 cube number of arithmetic operations. 1000 cube is 1 billion. So instead of 1 million, now you need 1 billion operations, which is still a big task, right? Still it will run very quickly, one solution. But remember that we may now need to do it for many time steps. So for example, our research students who are working on different area, say solidification or phase change materials, or alloy solidification, microstructure evolution. So generally, they will tell you that the number of time steps that are required for typical problem. For our cases, say if I consider typical, say, energy storage problem, I will have around 1 million time steps. So 1 million time steps are there, and it's a 3D problem, or a 2D or a 3D problem, not even 1D problem. Okay, so for each time step, you need to do this. So if it is, even if it is a 1D problem, you need 1 billion operations. So you can imagine how will it scale with 2D or 3D, right? It becomes a very difficult task to solve. So same thing now, if it is a 2D problem, or say it is a 3D problem, and I have 100 points along each direction. I have divided the domain into 100 points along each direction, which is typical. It is not a very, say, very defined grid. It is just a normal grid structure. But 100 point in each direction means how much? Total number of grid points or total number of control volume. It means that 100 cube, because it's a 3D volume, I have 1 million grid points. So now you can imagine the scenario. You have 1 million grid points. So 1 million equations for 1 million unknowns in each time step. And you have 1 million time steps also. So 1 million equations for 1 million unknowns you want to solve. And if you use Gaussian elimination, you will need number of arithmetic operations of the order of 1 million cube. How much is 1 million cube? It's a big number, right? 10 to the power 18. 1 billion billion. So you will need 1 billion operations just for one time step. So for 1 million time steps, you need 1 million billion operations. So it does not scale well. So it is which will take years or centuries, maybe, or like millenniums to run problem. So that is the main problem. Okay. So now what we see is that, say again, if I go back to this nice example, this was from finite difference, finite volume method also will show the same thing. What you see here is that matrix has a certain characteristic. It has only values along the diagonal lines, right? Along the three diagonals. So it is known as a tridiagonal matrix. Okay. And all the other values are zero. Only along the main diagonal and the two adjacent diagonal there are values. So we can use this extra characteristic, extra information that all the other values are zero to find the solution much faster. Okay. So we can reduce the number of iterations, so number of arithmetic steps to much less number. Okay. And this method that we are going to learn, tridiagonal matrix algorithm, takes of the order of n operations instead of n cube. Okay. Now you see the difference. If I have 1,000 points, I will need of the order of 1,000 arithmetic operations instead of 1 billion operations. If I had 1 million points, although I cannot use it for 2D and 3D, that will come later in the discussion. But say if I had 1 million points, then I would need 1 million arithmetic operations, which is nothing as compared to 1 million billion. So, or say 1 million operations per time step. So multiplied by number of times is 1 million more. So it is 1,000 billion, and that is feasible using now recent one, means the computing power that we have. It will take few minutes to run. But if you scale it to, if you use Gaussian elimination, it is beyond solution. In some cases, it is still useful, but there are better options. Okay. So for larger cases, what we do is we go for iterative solution instead of directly solving. So direct solution is beyond our scope. So we go for iterative solution when the number of points become too large. So that we will discuss later, but let us come back to this tridiagonal matrix algorithm. So huge reduction in computational cost from n cube to n, order of n, from order of n cube to order of n. So let us see how to do it. This is very widely used in many applications, means for solving any finite volume or finite difference method. Okay. So say we have a what we have seen equation of this form. Okay. APTP is equal to AT plus AWTW plus B. Okay. So this is similar to this form, AITI. So P is say ith grid point. Okay. So AITI is equal to BI. BI is for the ith grid point, the coefficient of I plus 1 variable. So this is AET, similar to AET. Okay, BITI plus 1 plus CITI minus 1. This is the waste term, W term, TW term. And we had written this as AW, but now for generalizing, we are writing it as CI. So all the coefficients are for the ith equation. We are trying to write the ith equation for the ith variable in terms of its neighboring variables. So AITI is equal to BITI plus 1 plus CITI minus 1 plus DI. This DI has all the other things like this source term. This is our equation for the ith grid point. And I can vary from 1 to n or 2 to n minus 1, depending on what type of boundary condition is given. We have discussed that. So we let us consider the general case that the boundary temperatures are also not known. So I can vary from 1 to n. So n equations will be there where I varies from 1 to n and n unknowns. Okay. So we want to solve this to find the value. Remember that this AI, BI, CI, and DI, these values are known already. How are these known? Like, what are the factors? Like, what will AI have in it? What will it depend on? AI, BI, CI. What factors will be there inside? What are the parameters that are required for finding AI, BI, CI, and DI? At this point, we already know what is AI, BI, CI, and DI. But how will we have calculated this? Based on what parameters?
Time step and spacing.
time step, and
Spacing.
grid spacing. Anything else? Say if it is only time step, use logic. Let us use logic. Say it is only time step and grid spacing. So it means that only TI only depends on the neighboring points based on time step and grid spacing. It does not have any information regarding heat transfer or whatever is occurring.
So the thermal conductivity will be there.
Conductivity has to be there, right? Conductivity, rho and Cp also will be there if it is an unsteady problem. Okay.
Yes, sir.
So some information needs to be there because it's a heat transfer. Similarly, for other cases, flow problem, there will be viscosity, things like that. Okay. So anyway, at this point, we already know that based on geometrical parameter and thermophysical parameters. Thermophysical parameters are the conductivity, density, then specific heat, things like that. Latent heat. For more complex problems, there may be latent heat, then enthalpy. Okay. No, not enthalpy. Enthalpy will come here. So latent heat and other things. And geometrical parameters, grid spacing, spacing between two grid points or control volume size. If it is a complex problem, maybe the other factors are also required. Okay. But ultimately, these are known. And for I is equal to 1, which is the leftmost side value, there is no I minus 1 value, right? So C1 is 0. So it's like this type. And for I is equal to n, there is no I plus 1 value. It is outside the domain. So Bn is also 0. Okay, so C1 is 0, Bn is 0. Okay. So now we want to solve this. So it involves two sets of actions. Okay. So TDMA involves what is known as forward elimination and backward substitution. Let us try to first, let me just go through it and then we will try to understand it. And then if you have any questions, you can ask. It's a very simple yet clever solution which gives us quickly the results. Okay, it was developed by Thomas. It is also known as Thomas algorithm. So say I can express, somehow I can express the ith grid point temperature Ti in terms of only the I plus 1 at grid point temperature, not the I minus 1. Only the I plus 1 at grid point temperature. So Pi, Ti plus 1 plus Qi. This Pi and Qi are unknown coefficient. Okay. At this point, we do not know. But say we are able to, we can write this in this form. Okay. Ti is equal to Pi, Ti plus 1 plus Qi. So this we can write, say, after we have already calculated, somehow we don't know yet how we have calculated, but somehow we have calculated Ti minus 1. Means we have written Ti, we don't know the value of Ti minus 1, but we have written it in terms of Ti minus 1 is equal to Pi minus 1 Ti plus Qi minus 1. Again, only based on the next value, okay, not the previous value. So Ti minus 1 is equal to Pi minus 1 Ti plus Qi minus 1. So when I say that we already know this after obtaining this, I mean that somehow we know the value of Pi minus 1 and Qi minus 1. We have done some operations to get this value. At this point, we do not know yet how we have got this, but we know that we know these values, Pi minus 1 and Qi minus 1. Obviously, Ti minus 1 and Ti are unknown. Okay. So if we know this Pi minus 1 and Qi minus 1, then we want to find out what is Pi and Qi. Okay, based on this information. And obviously, the original information is still there. That for any equation I, Aiti is equal to Biti plus 1 plus Citi minus 1 plus di. So based on this information. Okay. So now this equation for the ith grid point, I can write Aiti is equal to Biti plus 1 plus Ci. Instead of Ti minus 1, I will write this as Ti minus 1 is Pi minus 1 Ti plus Qi minus 1. If you don't follow, please ask questions. Okay. So Ci Pi minus 1 Ti plus Qi minus 1. Because we know, we are saying that Pi minus 1 and Qi minus 1 are known. Somehow it is known. I don't care right now how it is known, but it is known. Okay. Plus di. So obviously Ai, Bi, Ci and di are known, and I am also saying Pi minus 1 and Qi minus 1 are also known. Okay. So now we can rearrange the terms. So bring all the Ti terms to the left side. Okay. So Ai minus Ci Pi minus 1, okay, Ti, and bring all the Ti plus 1 to the right side is already there. So Bi Ti plus 1 plus whatever extra terms are there without temperature, which is Ciqi minus 1 plus Di. Okay. Now compare this equation with this equation. Ti is equal to Pi Ti plus 1 plus Qi. Okay. So we want to set this equation in this form. So what we will do? We will take this to the right hand side. So we will write this as Ti is equal to Bi by Ai minus Ci Pi minus 1, Ti plus 1. And for the next term, we will write it as plus Ciqi minus 1 plus Di divided by this Ai Ci minus 1 Pi Ci Pi minus 1. Okay. So this will be exactly of this form. Okay. Where Pi can be written as now. Just compare this. Pi is Bi divided by Ai minus Ci Pi minus 1. Okay. And Qi is without any temperature. So Qi is, so what is Pi? Pi is the coefficient of Pi plus 1, right? And Qi is without any temperature. So this is Ciqi minus 1 plus Di divided by Ai minus Ci Pi minus 1. Okay. So Bi is known, Ai is known, Ci is known, because we have already stated that these things will be known. Okay, these things will be known based on geometrical and thermophysical parameters. And Pi minus 1 and Pi minus 1, I am saying that we have somehow calculated. So at this point, it is known. I do not yet know. I am not telling yet how it is calculated, but it is calculated and it is known. Similarly, for Qi, I am telling that Qi minus 1 is already calculated, but we do not yet know how it is calculated, but it is calculated, it is known. So Ciqi minus 1 is known, Di is known, Ai minus Ci Pi minus 1 is also known. So we can find out Pi and Qi from these equations. Okay. So what is the significance of this set of operations that I have just described? The significance is that if you know Pi minus 1 and Qi minus 1, means if you know this equation, Pi minus 1, Qi minus 1, you can find out Pi and Qi. So we can proceed with increasing values of I if we can somehow know what is P1 and Q1. If we can know what is P1 and Q1, so then here I will put P1 and Q1, and I will find out P2 and Q2. Okay, because I will be 2. So for I is equal to 2, P2 is equal to B2 divided by A2 minus C2 P1. And Q2 will be C2 Q1 plus D2 divided by A2 minus C2 P1. Okay. So if I know P1 and Q1, obviously A2, B2, all these are known. All these coefficients are known based on thermophysical parameters and geometrical parameters. So if I know P1 and Q1, I can find P2 and Q2. And once I know P2 and Q2, I can then find P3 and Q3 from the same equation, same set of equations, similar equation. Okay. So here I will put P2 and here I will put Q2 and I will find P3 and Q3. So I can proceed like this until we reach Pn and Qn. So I will be able to find all the coefficients, all these new coefficients, Pi and Qi from 1 to n. Okay. So that is the idea. So now the task is that somehow I have to know these values. Okay. One set side value at least I need to know. P1 or P1, Q1 I need to know, or some value I need to know. Okay. So now the algorithm, let us discuss the algorithm. Okay. So this is known as forward elimination, what I have just described. Okay. I will come to backward substitution later. So what is the algorithm? Start from I is equal to 1. Okay. Let us look at this equation. A1 T1 is equal to B1 T2 plus C1 T0. T0 is not there because for I is equal to 1, C1 is not there. So this term is not there, plus D1. Okay. So A1 T1 is equal to B1 T2 plus D1. So from this equation, P1 is equal to B1 by A1 minus 0 because C1 is 0. Okay. So B1 by A1. And we do know B1 and A1, right? Because that is only just based on thermophysical parameters. So we do know B1 and A1, so we can calculate P1. Similarly, for this equation, this is 0, C1 is 0. So this is equal to D1 by A1 minus 0. So D1 by A1. And we do know again D1 and A1 based on thermophysical parameters and geometric parameters. So Q1 also can be calculated. Okay, A1, B1, and D1 are known. Just a second. So let us continue. So P1 and Q1 are found. Okay. Now let us proceed in the manner that I have suggested to you before. So once P1 and Q1 are known, now next I will go for I equal to 2. And for I equal to 2, P2 is equal to B2 by A2 minus C2 P1, and Q2 is equal to C2 Q1 plus D2 by A2 minus C2 P1. So B2, A2, C2 and D2, these are all known based on the coefficients calculated from the discretized equation. So now you understand the role of the discretization. Discretization is there to create these coefficients for all the equations. So for n equations, we are creating all the coefficients. We are calculating all the coefficients through discretization. Whether I use finite volume or finite difference, ultimately we will get some coefficients. Okay, I can use the same solver for solving the discretized equation, whether it is derived by finite volume method or finite difference method. Okay, so this part can be totally separate. Somebody else can also write the program for this, and you can just supply the A1, B1, C1, D1 values for all the I, means AI, BI, CI, DI values for all the n equations to her, and she can then just solve the equations based on that. So it can be a totally different part written by some, like another person also. So anyway, so P2 and Q2 can be calculated because P1 and Q1 are known, and similarly, based on P2 and Q2, you can calculate P3 and Q3, P4, Q4. Like this, we will proceed. So what is this called? It is called as forward elimination, right? So for any intermediate value of I, we can calculate based on Pi minus 1 and Qi minus 1, as I have already written, same thing. Okay, as Pi minus 1 and Qi minus 1 is already known from previous calculation. Now we know how we have obtained this. We have started from P1 and Q1 and found PUT, Q2, P3, Q3 like this until we reached Pi minus 1 and Qi minus 1. That is why we know these values, and now we are finding Pi and Qi. Okay, now Pi and Qi can be directly calculated. And this we will continue till I is equal to n. So with this process, we will know Pn minus 1 and Qn minus 1. And finally, for the final step, we will find what is Pn and Qn. Okay, we'll find what is Pn and Qn. However, what will be Pn? Let us look at the equation once more. For I is equal to n, Bn is 0, right? Because there is no Ti plus 1, that is outside the domain. So for I is equal to n, this is the last point. N point is the last point. So there is no point n plus 1, right? So Bn is 0. It means that from this expression, Pi, so Pn is equal to Bn by whatever is value. So because Bn is 0, Pn is also 0. Okay, so Pn is equal to 0. And what about Qn? Qn is Cn, okay, Qn minus 1 plus Dn divided by An plus Cn, An, Cn, sorry, this should be minus, right? Have I made some mistake? Okay. So Cn, what was the equation? Cn Qn minus 1 plus Dn by An minus Cn Pn minus 1. Okay, this will be minus, right? So Cn, Dn, An are known, right? Because these are the coefficients. Again, we know how to calculate the coefficients based on our whatever discretization method we choose. And Qn minus 1 and Pn minus 1 are known from previous calculation because we have started from P1 and Q1 and we have reached this point. So we can calculate Qn using this value. Okay. So Qn is known and Pn is known. Pn is equal to 0, Qn is known. Okay. Qn is also calculated. Okay. So we have found all the Pi and Qi values starting from I is equal to 1 to I equal to n. So forward elimination is complete. So now we will go for what is known as backward substitution. Okay. So now we know that for any ith equation, we can write Ti is equal to Pi Ti plus 1 plus Qi, right? Because this is the way we have started. So we have defined that Ti can be written as Pi Ti plus 1 plus Qi. Okay. That is how we have obtained all this Pn and Qn, right? So for I equal to n, Pn is 0. This also makes sense because Ti plus 1, there is no value, right? So already we have found Pn is 0. So Ti should be equal to Qi for I equal to n. So Tn equal to Qn. But now Qn is known. We have already calculated Qn. So it means that we can find what is Tn. Okay, from this. So now we know the temperature at the nth grid point. Now we will go in the backward direction. Till now we had proceeded in the forward direction. Now we will proceed in the backward direction. Using what? Using this set of equation. Okay, this equation. So we will use this equation to proceed. So once Tn is known, next we will go for I is equal to n minus 1. So Tn minus 1 will be Pn minus 1 Pn plus Qn minus 1. Okay. So Pn minus 1 and Qn minus 1 we have already calculated. All the Pi and Qi we have calculated. And Tn we have just now found that Tn equal to Qn. So we can find out Tn minus 1. Okay. So we will march backward in I. For any I, Ti is equal to Pi Ti plus 1 plus Qi. Okay. As Ti plus 1 is already calculated, Ti can be directly calculated. Okay. So that is what I was just explaining. For I is equal to n minus 1, Tn minus 1 is equal to Pn minus 1 Tn plus Qn minus 1. Tn we just calculated and Pn minus 1 and Qn minus 1 are known. All Pi and Qi are known. So now we have found Tn minus 1. Now we will find Tn minus 2. So Tn minus 2 will be Pn minus 2 into Tn minus 1 plus Qn minus 2. Now because we know Pn minus 2 and Qn minus 2 and Tn minus 1 we have just calculated, we will find Tn minus 2. And like this we will proceed in the backward direction until we find T1. Okay. So by marching backward in I, all the values of T can be calculated. This is known as backward substitution. Okay, this is the entire algorithm for TDMA. Okay, you can also try to write a code for this. It's quite interesting and very fast. This algorithm of the order of n operations. It does not mean it's equal to n. It can be say 6 times n operation, but order is n. If I increase the number of grid points by 10 times, the number of computational time, the amount of computational time will increase by 10 times. But in Gaussian elimination, if you increase the number of grids by 10 times, your computational time will increase by 1000 times. So in one case, if I take 1 hour to solve a problem and I refine the grid by 10 times, for TDMA it will take 10 hours. In the Gaussian elimination case, it will take 1000 hours, which is a huge amount of time, right? More than 1 month. So it's a totally different league. Any questions? Is this algorithm clear? You will be able to write a program on this. Very useful algorithm. Anyone is there for whom it is not clear how this works? New students? Dushyant, it is clear?
Yes, sir. It's clear, sir.
Okay, good. So very useful for 1D problems. Okay, why I am mentioning 1D? Because we will see that it cannot be used for 2D or 3D directly. Okay. So can directly solve all the discretized equations? Directly solve means no iterative, nothing, no approximation, right? Directly you are solving n equations to get n unknowns. Iteration is not required. Very fast. This is very fast as compared to other direct methods of matrix inversion. Number of operation is of the order of n instead of n cube, which is required for Gaussian elimination. Okay, that's why it is very useful. Now, why cannot I use it for directly use it for 2D or 3D problem? Say you want to use it for 2D problem. Where will you find the difficulty? New students who have not done CFD course. Ashraf, what will be the difficulty if I want to use it in 2D? Can you say? Madhumita? Priyal, you are there? Yes.
Yes, sir.
What will be the difficulty? Can you?
No, sir, I'm not getting.
Okay. So if it is a 2D problem, what will be the form of the equation? This equation. What will be the form of the equation? So I will have the ith value means it is a 2D, right? So let us go back to a 2D problem like this. So this P I will write in terms of what? I comma j. P is I comma j, right? So then the equation will be in terms of. So equation finally comes out as this. APTP equal to AET plus AWTW plus ANTN plus ASTS equal to plus B. Okay. So similarly, if you do finite difference also, you will see that AI, whatever is this, AIJ, TIJ will be AIJ means BIJ, whatever value you take, Ti plus 1j, Ti minus 1j, Tij plus 1, Tij minus 1. Okay. So if I write this in matrix form, how many diagonals will be there in the matrix? So I have in each equation how many unknown variables are there and how many coefficients are there. This b will go to the other side. Okay, but if I could write in this form, then I have a tridiagonal matrix. For this equation, how many diagonals will be non-zero? It's a very simple question. Shivam, you are there?
Yes, sir. Yes, sir.
Yes. What will be the answer?
Sir, for
What
each
2D problem, if I write, say, in terms of this matrix form, how many diagonals will be non-zero? Say this is a general equation, right? This multiplied by this. So 5 variable values will be there in one line, right? Which are
yes, sir, yes,
non-zero.
sir.
So it will be a 5 diagonals will be there non-zero, right? For each part, 5 variables will be non-zero. For 3D, how many will be there? Non-zero diagonals?
7.
7 non-zero diagonals. Okay. So because it is not a tridiagonal matrix anymore, you cannot use that tridiagonal matrix algorithm directly for 2D or 3D. Okay. So we will see later how to modify it so that we can still use TDMA, but that will require us iterations. Okay. What we will do is only for one line, means even if it is a 2D problem, only for one direction, one line, sorry, like this, one line, I will solve as a 1D. And then I will solve for the next line as a 1D problem, next line as a 1D problem. Like this, I will proceed. So that method is known as line by line TDMA, which we'll discuss later on. Okay. So that is the difficulty in using TDMA for 2D or 3D problems.
Sir, like once you have mentioned about this thing, like what can we do in order to increase the number of non-zero diagonals? There you mentioned that if we go for 2D or 3D problems, then we have some extra non-zero diagonals. So, like back then, you were saying that you will tell us later about these problems. So,
No, that is the same thing. Means I could not clearly understand your question, but the number of non-zero diagonals in 1D problem is 3, in 2D problem is 5, and in 3D problem is 7. Now, when it is 3 non-zero diagonals, you can directly solve it, and it will take of the order of n operations to solve it. But once you go with for 5 diagonals or 7 diagonals, you cannot directly solve this equation. You can obviously use Gaussian elimination, but that will take n cube number of steps to solve.
let's see.
So in that case, it is better to go for some iterative scheme. Okay, iterative scheme which we will discuss now. You have already studied most probably. You have taken CFD, right? But for others,
Yes,
will
yes.
be it will be new thing for you. It is just a revision. So we will see about some iterative schemes. So I will take a break here, 5 minutes, 5 to 10 minutes, and then we will continue. Okay. So let us continue. All right. So we will go into iterative methods, and these iterative methods are more suitable for 2D and 3D problems. Obviously, you can use for 1D problem also, but because we have such a nice TDMA method for 1D, generally that can be used for 1D. Okay. So efficient. Why we are going to use iterative methods for 2D or 3D? Because efficient methods which can directly solve the equation, such as TDMA, cannot be directly used for 2D or 3D problem. Okay. We need to modify it, and then with the modification, it will also become an iterative method. So it will be part of the iterative methods only. There are other direct methods such as Gaussian elimination, which are too slow, as we have already discussed in detail. Okay. So let us start with one method, okay, which is known as Jacobi method. So I will show you one example, and from this it will be clear how this works, and then it can be extended. This example can be extended to a general problem, generalized n number of equations. Okay. Very simple. It's very simple. This is nothing. So say there are two equations and two unknowns. 2x1 plus x2 is equal to 6, and x1 plus 3x2 is equal to 13. Okay. So what we do is that we find out using one of the equations, we find out one of the variables using previous iteration value of the other variable. All, if there are more than two variables, using previous iteration value of all the other variables. And similarly, from the other equation, we find out the other variable using previous iteration value of. So this we will find out using this value. Okay. So we can write x1 for the kth iteration. Okay. So x1 for the kth iteration is equal to 6 minus x2 divided by 2. From this equation, 6 minus x2 by 2. This x2 we will use from the previous iteration, which is already known to us at this point of time. Okay. So if we know the k minus 1 iteration value, we can find out kth iteration value of x1. Similarly, from the second iteration, second equation, we can write x2 to be equal to 13 minus x1 by 3. So x2 for the kth iteration is 13 minus x1 for the k minus 1 iteration, which we have already calculated in the previous iteration, divided by 3. So this is how we can calculate. So we will start from k equal to 1, and then k equal to 2, because k equal to 1 does not make any sense. So because k minus 1 is not there. So start from k equal to 2 and we'll proceed. How long will we proceed? When to determine to stop? Because we can go until k is equal to infinity, but there is no point. So how will we decide when to stop?
When x1 and x2 values doesn't change much.
Correct. So when x1 and x2 does not change much. So what is this much? This, like, how will we define much? So depending on our own criteria. So this is known as convergence criteria. Okay. When our solution is going towards the correct solution, we call that we are going towards convergence. And this convergence criteria can be, say, 10 to the power minus 3 in relative terms, or 10 to the power minus 6, 10 to the power minus 4, minus 5, whatever. It depends on how much accuracy you want. And accordingly, the value of k will also keep on increasing. If you want 10 to the power minus 6 accuracy, you will need a lot of iteration. If you need only 10 to the power minus 3 accuracy, you will need less iteration. Okay. At this point, it is important to actually specify here. Sometimes students get confused. Iteration is not equal to time steps. Okay, two are totally different things. In a single time step, you can have multiple iterations. So for example, to solve in a single time step, you will need to solve these n equations to get the n unknowns. What are the n unknowns? Say the temperature at n points for that time. Okay. So you can use either TDMA, or if it is a 2D method, 2D or 3D problem, you can use this Jacobi method. Okay. So, and for convergence to be achieved, say it needs 100 iterations or 50. I'm just giving some value, 50 iterations, 100, whatever, 100 iterations. So this is just for a single time step. If I have 1 lakh time steps or 100 time steps. Accordingly, for each time step I have to do, and for each time step it may take different number of iteration values. Okay. So sometimes what happens is that without understanding too much, students sometimes go for default values in the commercial software like ANSYS Fluent. Okay, where it is fixed as number of time step per number of iteration per time step to be 20. But this 20 iteration is not sufficient for the convergence to occur. So accordingly, we have to think about how many time iterations may be required. For some very non-linear problem, it may require large number of iterations to converge. For example, for one of my students who is working on laser melting, we are not getting correct solution after 1000 iteration per time step, but we are getting the correct convergence. Convergence is very slow. We are getting it after 5000 iteration per time step. So now we have to, so this 5000 iteration is required for each time step, and there are a large number of grid points because it's a 2D problem. So you need to solve, repeat again and again 5000 iterations. We do not need 5000, which is getting convergence 3000 or 4000 iterations. But for each time step, you need to do this. Okay, so time step is different number of time steps, and within a time step, then there are iterations. Okay, so there should be separate counters for this. When you are counting the number of iterations, if I am counting by k, so this will be for any particular time step. For the next time step, again k will start from 1 or 2. Anyway, so this is the method, basically very simple, right? So how will we start? We have to start from some initial guess. Now the question is, what should be the initial guess? So we can take any initial guess, but the convergence will depend on the convergence. Number of iterations required for convergence will depend on the initial guess. And sometimes it may happen that the solution can diverge also depending on the initial guess. But otherwise, most cases it will lead to the correct solution if you start with the initial guess. Okay, and whatever initial is the guess, only the number of iterations will be different. So if there is no other information, we can start with 0, 0 or 1, 1, whatever is. If we would have even started with 100, 100 also, still we will get the correct solution. Or any million, then also it may take more time, more iterations to get the correct solution, but we will achieve the correct solution. Okay. So there are better ways to take this initial guess. Okay. So for a transient problem, what will be a suitable initial guess? Say we are solving for temperature and velocity. So for a transient problem, time dependent problem, when I start the calculation for a new time, what will be a suitable initial guess? Can you have a better guess than the 0, which is very arbitrary? Yes? Tell.
So we can take the value of ambient temperature.
Ambient temperature. Why ambient temperature? Because say I'm solving for a application of furnace, melting in a furnace, which is very large temperature. You are saying the initial temperature, is it?
Yes, sir.
Can there be a better guess? Initial temperature can be a good guess, but can there be a better guess? We are starting a new time step, and I want to take the initial guess. Based on whatever we have calculated till then, what will be the best guess? Or what value should be the closest to this new value that we are trying to calculate? What known value? Ambient or initial temperature is may not be so close. So for example, if I am solving for a solidification casting problem, initial temperature was for liquid iron, it was say 2000 degrees centigrade. But gradually after solidification, it becomes only say 1200 degrees centigrade. So initial temperature is very far away in this case. So what is the best guess in that case? Think. What about the previous time step value? Final value in the previous time step, converged value. That should be the very good guess, right? Because in a time step, small changes occur. So we have already calculated previous time step value, maybe instead of 1200, maybe 1204 or whatever. So we can take that as a guess. We could have taken the initial temperature, but we can take that as a guess. And that should be a much better guess for starting the next time step iterations. Is it clear? Any confusion? Seems clear. What about, say, velocity I'm trying to calculate, and for the first time step, so there is no previous time step. How will I take the initial guess? I can take 0, obviously, but what can be a better guess than 0? Lot of intricacies are there in CFD, right? What can be a better guess than 0 for the first time step? Because I have not solved any previous time step, I do not have previous time step value.
Sir, could you please give us a situation where we need to find it? Then
Flow
it
in a pipe. Flow in a pipe I am trying to solve. Okay. And I have just started solving, and I want to solve the transient problem in flow in a pipe. So I have the one from one side, flow is coming with a certain mass flow rate, and it is going out on the other side because of pressure, some pressure. And I want to find out the velocity field in the pipe, how it is varying with time. So gradually the flow will stabilize with time, and it will lead to a steady state solution, but initially it will be unsteady. So how to solve that? First iteration.
Velocity at
initial
V3.
average velocity.
What velocity? What was the? I could not hear the answer. Two answers were there.
Sir, we can take initial average velocity.
What is initial average velocity?
So at which
How will you
like,
know what is initial? Because no one has given you the initial average velocity. Initial velocity where? In the domain. That has not been given to you, right? How will you know what is the initial velocity in the pipe? We will know whether it is static or not. What about the boundary velocity? So initial velocity also, then in that case I may have to guess. So that will depend on the boundary. So I can take a, say it is 100 meter per second at the inlet. I have calculated from the mass flow rate and area. I can take that as a better guess. So you can think cleverly to reduce the number of iterations and reduce the time required for solving a problem. We can always use brute force, like most of us do, like just take whatever 0, 0 value and try to solve it. But there are better ways to optimize, right? And it is important in many cases. Nowadays, with increasing computational power, it is becoming less important. But say when some years back, it used to be very important to actually see all this, how much is the computational efficiency, things like that. Anyway, coming back to this. So if we start with 0, 0, we are trying to solve this equation. So our iterative equations are this. So for the first iteration, for k equal to 2, 6 minus 0, because x2 we are taking as 0. 6 minus 0 by 2. Okay, so 6 by 2, which is 3. So our first value of x is 3. And similarly, for x2, 13 minus 0 by 3. So 13 by 3, 4.333. So after one iteration, we are getting 3 and 4.333. Okay. So now we can start, we can do the second iteration. The second iteration will be x1 for the next value of k. Okay. So if I call this as first iteration was 1th iteration, k equal to 1, then this is 0. So that's why I've written 0, x1 0, x2 0. So second iteration is x1 2. Okay, this will be 6 minus 4.333. divided by 2. So you will, if you calculate, you will get 0.834. Okay, similarly, x22 will be 13 minus 3 divided by 3. So 10 by 3, 3.333. Like this, if you keep on proceeding, you will get values like this. Okay, I have calculated. You can use a calculator to find this. And values will try towards, go towards the, like, the changes that occur in each iteration will be less. So here you see large changes occurring from 3 to 0.834. Then slightly smaller change, smaller change, smaller like this. So ultimately for this case, I have stopped when the change is less than 0.01. Okay. For both the equations, for all the equations we need convergence. If they only for one equation is not sufficient. So for example, for this case already the change was quite, for this case, no, still there was a lot of change. Okay, anyway, so when it is less than 0.01 for both the cases, I am stopping the iteration. I'm saying that it's converged. So in this case, my convergence criteria was 10 to the power minus 2, which is a very crude criteria. 1% error will be there. So when you are using a computer, you will have generally 10 to the power minus 5, minus 6, and it will take more iterations to solve this. Okay. So it should be clear how to use this. Okay. If I generalize this now, let us keep this open. If I have n equations and n unknowns, I can write them in the matrix form. A is the coefficient matrix. A into x is equal to b, right? We have seen already. Where we have seen, here we have seen. A into t is equal to some k, so the same thing. Okay. A into x equal to b. X are the unknowns. So for the ith equation, okay, so there are n equations, right? For the ith equation can be expressed in terms of all the variables, okay, going from 1 to n. So ith equation can be written as aij xj is equal to bi. Okay. So how will it look like? ai1 x1 plus ai2 x2 plus ai3 x3 plus ai4 x4 like this. Ain minus 1 xn minus 1 ain xn is equal to bn. So this will be one equation. Similarly, for any I, you will have an equation. So you will have n equations. For each equation, you will have n unknowns in each equation. Okay. So I can take out the ith value for the ith equation on one side. So ith value means j is equal to I. Okay, if j is equal to I, aii xi. Okay, so that I can take to one side, and all the on the other side we will have all the other terms except j equal to I. So j not equal to I, going from j equal to I to I equal to 1 to n. Sorry, j equal to 1 to n. Aij xj. Okay, so this equation can be written in, this term can be written as a sum of two terms, aii xi plus summation of j from 1 to n, j not equal to I, aij xj. We have just taken out the j equal to I term. All the other terms are present in the summation. This is equal to bi. So now I can take all of them to the other side except the ith term. So I can write this as aii xi is equal to bi minus summation of gi from 1 to n, j not equal to I, aij xj k minus 1. So using the previous iteration value, k minus 1 value for all the other terms, I will find the kth iteration value of this ith term. Okay. So this is for one variable from one equation. Because you have n equations, you can do this for all the n variables by varying I from 1 to n. So you will have n equation, n unknowns, and in each iteration you will update all these n variables. Once you get them, again you will update. Okay, so this is how it proceeds. Jacobi method. Any questions? Find out what is the order of convergence of this method. Oh, no, it's not required anyway. Okay. Convergence rate we will not study in this course. So Anyway, so this we can implement easily. Implementation is very easy, right? So next we will see a modification of this method, which will lead to faster convergence. Again, these things are very familiar to the CFD student. So we'll see that today, and then we will stop. So I have to go to the department. We have another set of presentation from 5:30. Okay, so let us start this next method. So what you can see here in the Jacobi method, although it's very simple, you can easily ask one question. That already, sir, I have found x1k from the previous iteration value of x2. So why I am not using the new value of x1? Why using the previous value? Because new value might be more accurate. So why I am using the previous value? Okay. So obviously we can use the new value. Okay, and if you use the new value, so whatever known values are there up to this point, so this will be the known value. Then this method is known as Gauss-Seidel method. Okay, so I am showing the same equations again. 2x1 plus x2 is equal to 6 and x1 plus 3x2 equal to 13. Now the iteration will be slightly different. Just what I have described. x1k is equal to 6 minus x2 k minus 1. Exactly same, because for x2 you have not yet found the new value. You only know the previous iteration value. So this line remains same, but for the next one already we have found x1k. So x2k is equal to 13 minus x1k. Instead of x1k minus 1, I will use the new value. Okay. So if I have n unknowns, for the ith unknown, I will use all the new iteration value from 1 to I minus 1. And all the old iteration value from I plus 1 to n. Okay, I will repeat again this point. If I have n unknowns and n equations, for the ith unknown, all the values from 1 to I minus 1 will be known, will be updated. Okay, will be the new values. So I will use those values. But all the values after this, starting from I plus 1 and going to n, will be the previous value because they have not been updated. So I will have to use the previous values. Okay. So again, if we proceed, similar method, similar manner, initial case if we take 0, 0. So after first iteration, x1k is equal to 6 minus 0 by 2 is 3. And x2k is, now we will use the updated value. Okay, we will not use 0. Instead, we will use 13 minus 3 by 3. So 13 minus 3 is 10. 10 by 3, 3.333. Okay. So next, we will use x1 is equal to 6 minus 3.333 by 2. So it comes out 1.34. So for x1 also it will be faster. Why? Because your x2 is going faster. You are calculating faster. So for the x1 calculation, you are getting a better value of x2 to calculate. Okay, you can see directly the comparison. Okay. So here we are getting after one iteration 1.334 and 3.889, which we had obtained after 3 and 4 iterations. Okay. So after this, if you continue, after 4 iterations, we reach 1.01. After 5 iterations, we reach 1.002 and 3.999. So we have converged based on our convergence criteria of 10 to the power minus 2. So we need less number of iterations because the information is traveling faster. So faster convergence is there in the Gauss-Seidel method. If you generalize now, for n unknowns and n equations, okay, again we can write like the previous case. Previous case was this: summation j equal to 1 to n aij xj is equal to bi. Okay, just a second. Okay, aij xj is equal to bi. Okay, summation. So for one equation, for the ith equation. Okay, so now I will divide it into 3 terms. Okay, what are the 3 terms? I can write from j equal to 1 to I minus 1. J equal to 1 to I minus 1. I have the updated values. Okay, already it is updated. So aij, xj, k, because kth iteration values are already known in this calculation. So then the ith value, so which is aii xi, k. Obviously, we are trying to find k, and then the I plus 1 to nth value. So j is equal to 1, I plus 1 to n, aij, xj, k minus 1, because these have not yet been calculated. Okay. So I can take this from 1 to I minus 1 and from I plus 1 to n to the other side. So only thing that will be left here is aii xi. Okay. So if I take the aii to the other side, I get xik is equal to summation j is equal to 1 to I minus 1 minus aij aii divided by aia xjk. Because up to this point, we have already calculated up to I minus 1. Okay. So we are now calculating the ith value. So these are all the updated value. And from I plus 1, we do not have updated values. So from j equal to I plus 1 to n, summation minus aij by aii xj k minus 1, previous values. Okay. Plus bi by aii, or I is equal to 1 to n. So this is the equation for the ith equation. This is the form for the ith equation. So starting from I is equal to 1 to n, you can use this to iterate and use your convergence criteria to find the correct value. We'll stop here today. This is not part of the syllabus, today's discussion. So after the midterm, you can learn about these things. Okay. If there is a problem on solving using finite difference or finite volume method, simple problems using 4 grid points or 5 grid points, you will get a set of equations. You do not need to use any of this method. You can just try to solve. Say you get a set of 3 equations, 3 unknown. Directly try to solve them. Okay, whatever like you solve generally using elimination equation. That is actually Gaussian elimination that you do, but using elimination you can try to solve. So we will stop the recording here. Leave here.